I'm building a mini grinding machine using a 12-volt brushed motor. Its power comes from a 12-volt supply, and I've added a switch to turn it on and off easily. But, wow, the motor spins way too fast. At this speed, it feels a bit dangerous if I only want to grind small parts. So, I need a speed control circuit, a device that can adjust the motor speed, so it can be used flexibly for many purposes, from sharpening blades to polishing tiny screws. To control the motor speed, the simplest idea, and probably what most people think of first, is to change the voltage applied to the motor. I already have an adjustable power supply, and yes, when I lower the voltage, the motor speed also goes down. This method works fine, but it has some big drawbacks. Those adjustable power supplies are bulky, expensive, and especially not suitable if you want to run the system on batteries. The next solution that many people think of is using a resistor. A resistor limits the current flowing into the motor. Sounds reasonable, right? As a result, the motor speed does go down, but if you measure the temperature of that resistor, you'll see it heats up very quickly. The energy that should have been used to spin the motor is instead turned into heat, so the efficiency is extremely low and wastes a lot of power. And even worse, if you want to vary the speed, you'd need a high-power potentiometer. If you try using a small one like this, it'll just go up in smoke. Another simple idea is to turn the motor on and off repeatedly. When it stays on longer, the motor spins faster. When it stays off longer, the motor slows down. Sounds reasonable, right? But if we try to switch it manually like this, it's clearly not practical. We need an electronic circuit that can do this automatically, much faster and far more stable. And that's exactly the principle of a PWM circuit, which stands for pulse width modulation. Instead of powering the motor continuously, the circuit turns the power on and off very quickly, hundreds or even thousands of times per second. If the on time is longer, the motor runs faster. If the on time is shorter, the motor runs slower. The average voltage supplied to the motor changes according to the pulse ratio, so we can control the speed without using bulky power supplies or wasteful resistors. To generate a PWM signal, the simplest way is to use an Arduino or a similar microcontroller, just a few lines of code and you're done. However, if you want a solution that doesn't require any programming, the NE555 timer IC is a perfect choice. With only a few resistors and capacitors, we can create a stable, efficient, and easily adjustable PWM signal. This is the NE555 IC, a very popular timer chip used in electronic circuits. It has 8 pins, and here is the internal block diagram. Pin number 1 is GND, it connects to ground. Pin number 8 is VCC, it connects to the positive supply. Inside the IC, there are 3 resistors, each with a value of 5 kilo ohms, connected in series from VCC down to GND. These resistors create 2 reference voltage levels. That's also why it's called the NE555, because of the 3 5K resistors inside. If I apply 12 volts to VCC, the voltage at the divider points will be around 8 volts and 4 volts. These are the reference levels used inside the IC to decide when the output should turn on or off. In the internal circuit, you can see that the second divider point is directly connected to pin number 5. That's the control voltage pin. If you measure the voltage at this pin, you'll get around 8 volts when VCC is 12 volts. Normally, if you don't use this pin, you should connect a small capacitor about 100 nanofarads from pin 5 to ground. This helps filter out noise and keeps the internal reference voltage stable. Pin number 4 is the reset pin. When this pin is pulled low, the IC stops working and resets to its initial state. In most circuits, the reset pin is connected directly to VCC so that the IC operates normally. Inside the NE555 IC, there are 2 comparators and 1 flip-flop block. This is the heart of the chip. The interaction between these blocks allows the NE555 to generate stable oscillations and control the output precisely. To really understand how this IC works, let's take a closer look at each part in detail. The flip-flop block has 2 input signals, SET and reset. The output signal from the flip-flop is split into 2 paths. The first path goes into a buffer circuit, which amplifies the current and sends it to pin number 3. This is the output pin, where we get the signal. Thanks to this buffer, the IC can provide up to about 200 milliamps of output current, enough to directly drive an LED, a small speaker, or an external power transistor. The second path goes through an inverter gate, and then to the discharge transistor. When the flip-flop output is at logic 0, the signal after the inverter becomes logic 1, causing the transistor to conduct. The collector terminal of this transistor is connected to pin number 7 of the IC, called the discharge pin. When pin 7 is pulled low to ground, the external capacitor connected to this pin will discharge through the transistor, and this is the discharge phase in the oscillation cycle of the NE555. The flip-flop block inside the NE555 IC works just like an SR latch, a set-reset latch. It has 2 input signals, set and reset, and 1 single output called Q. When the set signal goes to logic 1, the output Q is set to logic 1, a high level. Even if the SET signal returns to 0 afterward, the output remains unchanged. When the reset signal goes to logic 1, the output Q is cleared to logic 0, a low level. Similarly, when reset goes back to 0, the output stays at 0. You can imagine this flip-flop as 2 push buttons that remember their state. Press the set button, the light turns on, meaning Q equals 1. Press the reset button, the light turns off, meaning Q equals 0. And it will keep that state until the other button is pressed. Asterisk, asterisk. Besides the flip-flop, the NE555 IC also contains 2 voltage comparators and a voltage divider network made of 3 resistors, each with a value of 5 kiloohms, connected in series between VCC and ground. This resistor network creates 2 important reference voltage levels. The first level is 1/3 of VCC. The second level is 2/3 of VCC. These 2 reference voltages are fed into the inputs of the 2 comparators, and they are used as thresholds to compare with the voltage across the external timing capacitor. The inverting input of the first comparator is connected to pin number 2 of the IC, called the trigger pin. When the voltage at this pin drops below 1/3 of VCC, the comparator outputs a high level, which activates the set signal for the flip-flop. The non-inverting input, that is, the plus input of the second comparator, is connected to pin number 6, called the threshold pin. When the voltage at this pin rises above 2/3 of VCC, the comparator outputs a high level, triggering the reset signal of the flip-flop. Now, let's go back to the simple oscillator circuit made with 2 resistors, R1 and R2, and 1 capacitor, C1. Here's how the connections are made. R1 connects from VCC to pin number 7, the discharge pin. R2 connects from pin 7 to pins 2 and 6, which are tied together. The capacitor C1 connects from pins 2 and 6 down to ground. Let's see how the circuit works assuming VCC equals 12 volts. At the beginning, capacitor C1 is not charged, so its voltage is less than 1/3 of VCC, about 4 volts. The lower comparator then outputs a set signal equal to 1, which makes the flip-flop output Q equal to 1. This drives the output pin, pin number 3, to logic high, and the discharge transistor is turned off. At this time, the capacitor starts charging through R1 and R2. As the voltage on the capacitor increases and passes 1/3 of VCC, the set signal goes back to 0, but the flip-flop output Q remains at 1. The capacitor continues charging through R1 and R2. When the voltage on the capacitor exceeds 2/3 of VCC, around 8 volts, the upper comparator outputs a reset signal equal to 1. This sets Q to 0, the output goes low, and the discharge transistor turns on. Now, the capacitor discharges through R2, and the transistor down to ground. When the voltage drops below 1/3 of VCC again, the lower comparator sends another set signal, making Q equal to 1 once more. The transistor turns off, the capacitor starts charging again through R1 and R2, and the entire process repeats continuously. The charging path through R1 plus R2 and the discharging path through R2 create a square wave output at pin number 3. This waveform is the oscillation signal we can use for PWM circuits, or motor speed control. Asterisk. Asterisk. All right, now let's build the actual circuit and test it in real life. Let's see if it works just like the theory says. Wow, it's working. The LED is blinking, but the speed seems quite slow. With this pulse frequency, it's not really suitable for motor speed control, because for smooth PWM control, the frequency usually needs to be in the range of a few hundred hertz to several kilohertz. So, to increase the oscillation frequency, I'll try reducing the value of capacitor C1 and see how it affects the result. Now we can see that the LED no longer blinks, and when checked with the oscilloscope, the frequency is measured at about 336 Hz. This frequency is fairly acceptable for motor speed control. However, there's one issue. The waveform is not symmetrical. The on time and off time are not equal. Why does this happen? If we look back at the circuit diagram, we can see that the charging time of the capacitor corresponds to the Higg period of the output pulse. The discharging time corresponds to the low period. During charging, the capacitor is charged through both R1 and R2 in series. But during discharging, it only discharges through R2 via the discharge transistor. Therefore, the charging time is longer than the discharging time, which makes the waveform uneven. So how can we make the charge and discharge times equal? The solution is very simple. Add a diode in parallel with R2. This way, during the charging phase, current will flow through the diode instead of R2, effectively bypassing R2 while charging. If we choose R1 equals R2, the charge and discharge times will become nearly equal, and the resulting waveform will be much more symmetrical. Awesome! We've successfully created a clean square wave. But now the question is, how can we change the pulse width, also known as the duty cycle? The solution is to add a potentiometer and two diodes, connected as shown in this schematic. Here's how it works. The charging time of the capacitor is determined by the left half of the potentiometer. The discharging time is determined by the right half. The two diodes on each side separate the charging and discharging paths, so when we turn the potentiometer, the charge and discharge times change independently. What's interesting is that the total resistance of the potentiometer remains the same. So the overall period, charge time plus discharge time, stays nearly constant. Only the ratio between on and off time changes. And that's exactly how we adjust the duty cycle without changing the frequency. Pretty clever design, isn't it? My circuit still had a small problem. When I turned the potentiometer all the way toward the smallest duty direction, the minimum duty I could get was only about 20%. It could not go any lower. The reason was that resistor R1 was still too large, so even when the potentiometer was at its minimum value, the capacitor still had to charge through R1. That limited the minimum charging time, and therefore the duty could not be reduced further. To fix this, I replaced R1 with a smaller resistor of about 470 ohms. After replacing it and rechecking on the oscilloscope, we saw that the adjustable duty range became much wider, and now the PWM circuit works complete, stable, and smooth. The output signal from the NE555 can supply a maximum current of about 200 milliamps, which is not enough to drive a motor directly. Therefore, to control a higher power motor, we need an additional current amplification stage, usually a transistor or a MOSFET. The NE555 will only generate the PWM control signal, while the transistor or MOSFET will handle the main current switching that powers the motor. Thanks to this setup, we can control the motor speed smoothly without overloading the IC. At this point, the circuit is relatively complex, so I will solder it onto a through-hole PCB to make it more solid and neat. Let's get to it. This is the complete circuit diagram. There's one very important thing to keep in mind. When your load is a motor or any device that contains a coil, you must add a protection diode. This diode is connected in parallel with the load, but in the reverse direction to the supply current. The reason is that when the power is suddenly switched off, the coil inside the motor generates a large reverse voltage, which can damage the MOSFET or the control IC. The protection diode safely redirects this reverse current back to the power supply, keeping the circuit safe and reliable. And here's the real test result. As I turn the potentiometer, you can see the motor speed changes smoothly with the PWM duty cycle. At a low duty, the motor spins slowly, and when I increase the duty, it speeds up noticeably. Everything runs stable, without any jerking or vibration. So the circuit works exactly as we expected. Pretty awesome, right? And that's it. We've successfully built a motor speed controller using the NE555 timer IC. From generating PWM signals, adjusting the duty cycle, to amplifying power with a MOSFET, everything works smoothly and efficiently. If you found this video helpful, don't forget to like, subscribe, and turn on the notification bell so you won't miss my next electronics tutorials. Thanks for watching. See you in the next video.